Morning, guys. So yesterday we started looking at the Bohr model. We know how to count protons, neutrons, and electrons. The Bohr model basically helps us because electrons have a negative charge. They always want to go closest to the core if they can. What Bohr had discovered was, for some reason in this quantum world, quantum mechanics here, there was some limit to how many electrons each of these shells can hold. First shell is tiny, it can only hold 2. Next shell can hold 8. The third shell you can say 8 or 18. We'll come back to that in a later lesson. So we have this sort of competition as electrons slowly enter into the different shells. They sort of don't like sitting by each other because negative hates negative, and yet the compromise that we always see is they always want to get close to the core. The closer they are to the core, they actually the more stable they actually get. So we basically do electrons, they enter the lowest shell first. We then introduce a few new conclusions. In fact, every single element actually had an infinite number of shells available. You could technically be on shell 1,000 or shell 1,000,000. And yet, because the atom only has so many protons in the core, there's a limit to how much attraction, how far away these electrons can get. Basically, the farther away things get, the physicists would tell us, well, the charges don't see each other as well, the attraction is not strong enough, that electron will actually be dislodged. We're going to come back to analyzing that energy level diagram more in today's lesson. We'll talk about what Bohr did to actually find these discrete readings here. We're actually going to get to see some of the nice spectra that get produced. Just before we get to that, however, I want to do a quick detour. I'm going to switch over to take a look at the electromagnetic spectrum. I think you were first introduced to this back in grade 8, but we're just going to rehash this. So electromagnetic spectrum here, spectrum just means a spread, and electromagnetic here, really the only example of electromagnetic spectrum we have is light, and all the different forms that light occurs in. When we say light here, turns out the visible portion of the spectrum is actually just a really narrow band in the middle of the spectrum here. We're going to have the one side, our rainbow is always colored in this order here, so if you have colors you can do it Roy, G, Biv, like this. So the colors that we can see, especially when there is a rainbow here, in that ordering here, turns out to actually only be a very narrow band in a much wider spectrum. I'm going to call that the visible region. We don't need any other technology. We can see this. In fact, usually when light comes to us as white light, it's sort of a combination of all these colors together. When these constructively interfere, they just appear white to us. But at least this band here of colors, this is the part that we can see. We're going to see that the red side, in terms of a wavelength, we'll talk about this physics in just a second here. We can actually measure it roughly on the 700 nanometer side. The purple, or sometimes they just call it the blue end or violet end. The violet end is going to be 400 nanometers. Again, we'll come back to what are we actually measuring, but roughly 700 side, 400 side. For the electromagnetic spectrum, like we mentioned, it's a much wider spread. There's actually other form of light. They just might not be visible to us with our naked eye. So let's look at the energies that are actually smaller than the visible. On the red side, if we go into the red, this region here, we're going to call it infrared. So it's going to be IR radiation. Every time when I see this word here, I always want to say infrared. Just remember, it's infrared. It's into the red region. This one here would be sort of, if you see movies with like thermal imaging, thermal goggles, when there's bodies that are warm, they glow orange and yellow. That's infrared radiation. If you didn't have the right thermal goggles, you couldn't see that radiation. But it is still a form of light, so it's IR radiation. If you keep going lower than that here, we use these waves a lot here to heat up our food, microwaves. Microwaves here are sensitive to polar molecules. Water molecules start dancing around a little bit faster because that's exactly the right energy that you need. And if you keep going down from there here, we're going to eventually have an overlap of radio. Definitely not evenly spaced here, and there's definitely some overlap with where does radio actually cross over in micro, but basically it's a rough ballpark. There are some forms of light that are actually less energetic than the red side. What about on the other side? Purple was already the high energy side here. What if I go beyond the purple? That's what we get here is actually UV light. UV light here is actually called ultraviolet. It's beyond the violet side, beyond the purple. It's going to have wavelengths even shorter than 400. As you keep going beyond there, you're going to get into X-rays. If you ever had to get an X-ray here, basically X-rays are energetic enough to get through your soft tissue. They reflect off your bones as if it's light off a mirror, and basically by sensing where those X-rays end up, we can get a nice imaging of your skeleton structure. So UV rays, they did call them X-rays because at first they really didn't know what they were. And then as we go up from there here, we go back to our sort of nuclear lesson here, we get to gamma radiation. So gamma radiation is the most energetic. We do use it for chemotherapy because it's really energetic. Hopefully it kills cancerous cells there. The hard part is the radiation here is not really specific. So many times it kills the cancerous cells, but it kills a lot of good cells. We're sort of crossing our fingers and we're sort of saying, I hope we kill more of the bad cells. We leave enough of the good cells so that they can replicate and they can sort of replace the cancerous cells. So that's what's called the electromagnetic spectrum here. I do want to take a quick detour into the physics, just revisit some of the language behind what is wavelength, what are we actually measuring, labeling, because we need some of these concepts in today's lesson. We have all these different forms. They're all part of the electromagnetic spectrum. What's important for you to note here is all, I'm going to call them EM waves, whether I'm a radio wave or a light wave, visible, purple, it doesn't matter. All EM waves travel at the speed of light, right? It's like light travels at light speed. Great. We're going to actually give this light speed here a constant here, c, and that's actually going to be 3.0 times 10 to the 8. Definitely a rounded number. It's like 2.99, something like that. So 3 times 10 to the 8 works good for us. What's implied by c here is not only is it a constant, in physics we do with relativity, things get really weird when we travel close to the speed of light. Time tends to slow down. It's like masses tend to increase. Lengths tend to get shorter. Speed of light sort of represents a maximum speed, and all of these light forms here travel at speed of light. Doesn't matter if I'm low energy like a radio wave, doesn't matter if I'm high energy like a gamma radiation. They all travel at the speed of light. So it's not the speed that actually sets them apart. This C here actually assumes travel in vacuum, so traveling through nothingness. So especially in physics 11, you might talk about, well, as light enters different media, different atmospheres here, it might actually slow down when it goes into water. That's what actually gives rise to reflection, refraction, all those concepts. For us, we're just going to treat it as some maximum constant. This, unfortunately, doesn't differentiate for us. Well, what makes microwave different from X-ray if they both travel at the same rate? We've already referred to it here as the amount of energy. The radio wave here is the low energy side. The gamma ray radiation here is the high energy side. So what we can do is we can do by arrow. Even though they all travel at the speed of light, we can point an arrow. We can say, based on the way I've listed it, you actually have increasing energy. So higher energy as you go to the right. We'll see a formula for that. And we're going to introduce, as we look at these wave terms here, we're going to introduce terms like amplitude, frequency, wavelength, things like that. Those are another two measures that we can measure for energy. As the energy gets bigger, we're going to be qualifying that in this lesson. We're going to qualify it. Frequency is actually proportional to energy. So if I point to the high energy side, we also have a higher frequency. I'll describe what that means in a second here. And we're going to find frequency and wavelength are actually opposite of each other. As you go in the direction that I've listed for you here, we're actually getting lower or shorter wavelengths. We're getting tinier in the gaps. So I want to just take a quick detour. I want to make sure you're familiar with this language here. We're not going to go too far into the physics, but just as it pertains to this Bohr model stuff. So as we take a look at just a general wave, let's imagine I go down to the pier and I take a picture of water waves. So maybe it's a very wavy day that day. What a wave is basically periodic motion. It's basically a part of the wave here. It's sort of like taking this part here, copy and paste it. It just repeats over and over again. So all this is here is a static picture of the wave here. There's already some terminology for us. The tops of these waves here, we can refer to them as crests. They're sometimes called the maxima because they're the maximum of the wave. They're the absolute highest the waves get to. The bottom of the waves here, we're going to call them troughs. Spelled troughs. So troughs, these ones can be called minima. Let's imagine the no wave case. So if it was a really steady day on the ocean, you can call that the equilibrium line or even the rest line. Just put EQM for equilibrium. I can measure the distance from this equilibrium line to the top or to the bottom. That distance there is referred to as the amplitude, the size of the wave. Amplitude, you can use A for it. Amplitude here is the distance from that equilibrium rest line, rest to the crest or even to the trough. It basically measures how big are these waves just from that middle point here. This one here is going to be related in terms of energy. So in your physics classes, the whole point of a wave is to actually transfer energy here. The bigger the amplitude, in the sound analogy, this would amount to a louder volume or softer volume for smaller amplitude. In the light case here, it would amount to a brighter color light or not as intense of light. So that's how amplitude works out. Because the wave here is actually a periodic graph, because it copies itself, there's no real point in measuring, well, how long is the actual wave itself? What I'm going to do is I'm just going to try to figure out how long is one of these segments. One of these portions that if I can copy and paste, let's say for example here, let's say I start here, it goes up, comes down, and comes back up. If I took just that portion as the length of the wave, I can cut and paste that portion, and that would overlap exactly with the next segment and the next segment here. I'm actually going to call that segment there the wavelength. So I'm just going to label over here. So we're going to call this here wavelength. Wavelength, we use a funny symbol, it's lambda. So Greek lambda. Right. And that's going to be a measure of distance, it's going to be in meters. And it's just going to be a measure, basically the distance before the wave repeats itself, just for convenience here, because it's a little bit weird. It's like, oh, it goes up, go down, oh, skip this point here, it hasn't repeated yet. It's a little bit hard. What they do is they actually usually say, well, the crest is usually really easy to find. This crest is really easy to find. You would definitely have to have made it all the way down and all the way back up. You would definitely have to complete one whole cycle for you to travel the wavelength. So usually for wavelength, they just refer to the crest to crest distance. Or it could be trough to trough distance, whatever is easy for you to measure. That 700 and the 400 that I listed for you earlier is this wavelength. So earlier when I said here, the 700 nanometers, that was sort of the red light, red wavelength. If I have a red laser pointer or whatever, and if it has a wavelength of 700, I'm saying, although light does travel in a straight line, these sort of red color photon, we call them little photons or packets of energy. Photons are sort of packets of energy. If I could represent the amount of energy that these photons, these packets carry, if I can represent it with a metaphorical wave, the waves themselves would actually be oscillating magnetic and electric fields if you go on to science. But if I can measure the crest to crest distance, this is actually in the order of nanometers. So let's take that apart here. Nano, hopefully you remember your prefaces. Nano means times 10 to the negative 9. So it's a billionth of a meter. It's just that when you type that in your calculator, notice I still have hundreds of a nanometer. Your calculator would write that 7 times 10 to the negative 7. That's totally okay. Right? It's trying to put it back in proper scientific notation for you. So the first digit is between 1 and 9. So it's not like the red photon actually literally is zigzagging back and forth. It's just the fields that are doing that. But I'm representing in this fashion here to show you how much energy this red photon is carrying. Let's contrast that with the purple photon. The purple wavelength here is 400. This 700 and 400 are very rough ballpark numbers. So 399 would still be purple, 390 would probably still be purple, but it gives us a rough estimate of where the visible spectrum starts and finishes. For the violet end here, this same wavelength is actually a lot tighter. It's about half the wavelength. Again, it's not really that the purple color light is actually zigzagging back and forth. The purple photons are just traveling in a straight line. But if I represent its wavelength here, you'll notice this wavelength here is a little more narrow than what it was earlier. It's about half what it was before. So that's what wavelength is measuring. It's the distance between crest to crest. This next part here is going to be a little bit confusing. If we go back to the water analogy, if we go back, these are actually literal waterways. I can see the tops of the waves and bottom of the waves. What I'm going to do is I'm going to imagine you're sitting on a boat, and let's imagine you're just sitting, minding your own business, you're at the rest line. What I'm going to plot this time is I'm going to plot how far up your water wave gets, or in this case your electric field oscillates in one direction. But what I'm going to do is I'm actually going to plot against time. Earlier what I did is I plotted it as like a photograph. It's like, here's the vertical and here's the horizontal. Here's what the water wave looked like. That is a still frame. That is a still picture. But what I'm plotting here, you can't actually take a camera of this one here. This one, I'm just staring at my clock. At 0 seconds, I happen to be at the rest line. So that's 0 seconds. As time pushes forwards, if you have different colors, it might help you here. As time pushes forwards, this wave here, let's say for argument's sake, it's actually traveling to the right. This wave here would actually push past you. And what's going to happen is you're going to be a little bit higher as time goes onwards. That means a little bit higher. Then what's going to happen is the wave's going to keep pushing past you here. All that's going to happen to you is you're going to gradually, you bobbed up with the wave as it passed you. As it gets to blue, it's going to start bobbing downwards. As it goes to, let's draw one more here. As it goes even past you even more, now I'm going to follow the bottom part of the wave. I'm actually going to fall downwards. on this metaphorical boat, I'm just going to end up bobbing up and down as time goes onwards. The confusing thing here is the shape of the graph here actually ends up looking identical. We call this a sinusoidal wave, a sinusoidal shape. But this time, again, I want to emphasize I'm plotting against time. This time you can't take a picture of this. This time I'm just staring at my clock. As the wave actually pushes past you, I want to track your motion up and down. This would be what's referred to as a transverse wave because the particles are actually going perpendicular to the way that the light photon is actually going. This time you can still label, yeah, crest, trough, and whatnot. But this time be really careful. If I actually measured what's this interval between this peak and this peak, this time it's not a distance anymore. It's not a length. This time it's actually a time. You can actually write that down here. We actually call this term here the period. Period, we're going to use capital T for it here. This is actually the time for one cycle. It's the time for one complete wave to pass by. If I started off with this first wave here, this first wave, this first picture here, that wave here would have pushed on past you, and now we're actually facing the next wave. We're ready to repeat again. The time for you to bob fully up, down, and then back to the start, that's called the period, and this is going to be measured in seconds. So that there is the period. What we're going to do instead, period is not super convenient to work with. What we instead do is we define one last concept here called frequency. Frequency, it'd be nice if they just use F. Many times, however, they use the Greek letter nu. It's like a sort of U with a longer tail. So that's Greek for nu, lots of Greek letters here. And basically the frequency is defined as the reverse of this period. It's the upside down of this period, reciprocal of this period. So the longer the period is, the longer it takes you to bob up, down, and then back to the top, the lower the frequency. The frequency actually tells you, I don't have all day, right? I don't have the time. Let's say it takes a minute for a whole cycle to pass by. Instead, what I'm going to do is I'm only going to give you 1 second. 1 second here is a fairly convenient increment. All I'm going to track is how many times do I bob up and down in that 1 second of time. So how many part cycles would I get? For every second. So the unit here is actually going to be a per second, and we're actually going to use hertz for a nice metaphorical, for a better unit of it. So on this metaphorical wave here, I know the red photon isn't actually zigzagging back and forth. The red photon is just going straight. You'll notice here, because the wavelength, because the distance to distance is actually really, really close, and because this is light and it zips by you, you're going to be hanging on for dear life. You're going to go up and down. Every time you go up and down once, that's one frequency, that's one cycle. You're going to bob up and down on the order of millions or billions of time in every second, because the wavelength is so narrow. The frequency, however, for the purple light will be even faster. The speed is still the same, but it's not taking as far for the peak-to-peak distance, and therefore, as you bob up and down, you're going to bob up and down so many more times just because the two crests is closer together. So, frequency here is somehow related to the energy as well. Again, in the sound analogy, frequency will give you the pitch, it's going to give you the note. In the light analogy here, we're seeing the frequency is actually changing color of light. So with that background of physics, let me introduce to you our two main formulas, and then we'll get back to the Bohr model here. The part that we're really concerned about here is our two formulas. First sort of wave formula we need is something called the universal wave equation, also on your formula sheet. In fact, the universal wave equation says V is equal to F times lambda, or lambda nu if you like. And for us, just for simplicity, although this is universal, this applies to all types of waves, water waves, sound waves, whatever, we're just going to use light waves. So we're going to simplify that, and we're actually going to use C is equal to F lambda. Just to get you used to the terminology here, I might even put that nu symbol. The nu is frequency, and then we have lambda. So let me just derive these terms for you here. This is the speed of light. The speed of light here, we know the number. That's on your data booklet, 3 times 10 to the 8. That already is our SI unit. This one here, what's important for you to know is not only is this a max speed, this is constant. What this constant here is made up of is it's made up of the wavelength, so lambda. How far is the crest-to-crest distance? This one here has to be in meters. And then what we're going to tack onto it here is frequency. And frequency here is going to be in the units per seconds. Again, we can call that hertz just for convenience, Hz. And therefore, if I just do dimensional analysis here, I take something in meters, I multiply something in per second, that's why I get meters per second. what this actually says here, if I just translate that into words, it says the wavelength and the frequency are actually inversely related. They're actually opposites of each other. Inversely related. How do I know they're the opposites? It's because they always need to multiply to give the same number. So as I go from, let's say, 700 nanometer red light to 400 nanometer light, as this number gets tinier, for two numbers to multiply to give the same number, the frequency has to go up. I'm going to bob up and down way more times because the crest to crest is so close together. That's the first formula. So that gives us a link between wavelength and the frequency. These are opposites. The other equation here is called the Planck equation. I'll do a quick example of these two equations. They're not that hard to work with, but they do have that little bit of background of physics that we just talked about. The Planck equation actually says, I can do it in words first. It says to us that the energy, waves are supposed to transfer energy from one place to the other, the energy is actually proportional or directly related, proportional to the frequency. So once you're able to count the metaphorical times you bob up and down as the waves pass you, the more times you bob up and down, the more energy actually is carried. So it's proportional through Planck's constant. The energy of a photon is through Planck's constant h and f. This one here is going to be energy. The SI unit here is going to be the joule. Planck's constant also in your data booklet, 6.63. Lots of constants in this section, by the way. So 6.63 times 10 to the negative 34. That's going to be joule seconds. And then this F here is the frequency that we saw from before. Frequency was in a per second. Sorry, I just noticed here. Planck's constant has to actually be joule multiplied by second. So that multiplies a second to minus 1 and it cancels out. All right. So just to introduce some of the vocabulary to you here, I'm going to give you a quick practice question. I want you to calculate the period. That's just for completeness sake. Calculate the period, the frequency, and the energy for a red photon. I could have chosen anything. I could have chosen a radio wave or whatever, but I happen to know red photon with wavelength 656. So our red laser pointers here happen to be 656. All right. So let's look at the formula so far. I told you the main focus for our chemistry course, we're going to use C equals F lambda, and we're going to use energy is equal to proportion to frequency. Just for completeness sake here, I actually threw in the period as well. Period is the 1 over frequency as well. Well, this question here, let's see. We have the lambda, so we have the wavelength. We know the speed of light is constant, so I actually have this number, 3 times 10 to the 8. What I can do is I can use this middle formula. I can first find frequency. Once I have the frequency, it's pretty easy to just take the reciprocal of that. I can get the period. Once I have the frequency, I can also multiply through Planck's constant, and I got the energy. And there you go. That's all you need to do. So speed of light is c, 3 times 10 to the 8. I already wrote that down for you. I don't know what the f is. The wavelength, just careful, it has to be in the correct SI units. 656 nano is 10 to the negative 9. You can type it in like that, 656 times 10 to the negative 9, or proper scientific notation, 6.56 times 10 to the negative 7. Do the division over, 3e8 divided by 656e negative 9. It tells me how many times do I bob up and down. I bob up and down 4.6 times 10 to the 14 hertz. If you give me 1 second of time, that's a ton of time. First things, light is traveling at a ridiculous speed, it's zipping by you, and because the distance between one peak to the other peak is not that far away, I'm going to bob up and down way more times. So I'm more than hundreds of trillions of times, so 10 to the 14. So there we go, that's the frequency. If you wanted to calculate the period, all you need to do is to take the reciprocal of this. 1 over the frequency is equal to 4.6 times 10 to the 14. The period is therefore 1 over this answer. This is going to be 2.2 times 10 to the negative 15. Period is a time, so this is going to be measured in seconds. Because if you give me 1 whole second, I'm going to bob up and down trillions and trillions of time. I only need sort of a fraction of a second for you to bob up and down just once. That's what period gives you. More important for us here is once you know the frequency, you know how much energy is carried. If I want to convert it back to my convenient unit for energy, I just need to multiply it through Planck's constant. 6.63 times 10 to the negative 34, and I'm going to multiply this frequency again. You see, once you find frequency, you can get all these other numbers. Sorry, this is for 0.6. Keep it unrounded if you can. That's going to be in hertz. and then I'm going to multiply through Planck's constant. So 4.6 e negative E14 times it by Planck's constant 6.63 e negative 34. This gives me here 3.0 times 10 to the negative 19, and that would have converted back us in SI unit joules. That's the energy unit for joules. So we have that there. You're going to notice, first thing in general, we had defined, unfortunately, when this science is developing, the joule, the coulomb, they themselves happen to be very big units. So that way, the numbers that happen to be with joules happen to be really tiny. We can switch over to electron volt to be a little bit easier later on. But more so here, this is the energy for one photon. So this is the energy for one single photon. As you have your laser pointer, you're probably going to have a whole stream of photons. If every single one of those carried 10 to the negative 19, let's say for argument's sake here I had a mole of particles, you'll see that the mole is actually 10 to 23. It's going to stack up this energy quite quickly. I didn't ask you for this here, but if I want to know how much energy does a mole actually carry, if I start scaling it up by a mole, this energy gets up to very, very high very quickly. So I'm getting here roughly 1.8 times 10 to the 5 joules. So that's sort of a reason why it's okay to keep the joule unit so big so that the number that we're carrying around is really tiny. Right? So on your worksheet, you're going to get some practice with dealing with these wave equations, converting frequency to period and whatnot. I just needed to introduce some of the vocabulary to you. You might be wondering, well, why did we do this? Right? I thought we were talking about the Bohr model. Now we can finally get back to it here. We're going to use the lens here. We're going to start off, as we start taking a look at the spectrum, we've already drew the EM spectrum. That was our continuous spectrum. If in this section here, if it asks you to define continuous spectra, you cannot say, oh, it's a spectra that's continuous. You can't define it with the same wording. What you can do, however, is you can say, well, spectra is plural for spectrum. Spectra usually means it's a spread. And in this case here, it's a spread of different wavelengths, it's a spread of different colors. For the colors to be continuous, it means that there's no breaks. So you can say spread of colors, or more generally, spread of wavelengths. You can say you can say all colors if you like. There's no colors missing, right? So that's a continuous spectra here. A source that does continuous spectra, let's pretend we send in white light. Let's send it in an angle from a prism. The prism will cause the waves to actually diffract, to actually bend. Depending on your wavelength, the wavelengths actually, they diffract at a different angle, and that'll actually separate white into all its different colors. So it's always going to be sort of in the order Roy G. Biv. We're going to pull out a device called a spectroscope, and basically what that spectroscope is going to show you is this is a continuous spectra. The red just sort of merges into the yellow, sort of merges into the green. Note these are not evenly spaced here. It's not like an even amount of every single color, but at least the relative ordering is always following that Roy G. Biv. This is a continuous spectra because you see that there's no breaks, there's nothing missing. This was actually hinting at Bohr model. Remember I was saying, how did Bohr know that energy shells are discrete? Why is it the staircase and whatnot? What he did is he actually, instead of testing white light, he actually used an element as his light source. And he put it through a spectroscope here. Spectroscope here is the name of the device that can actually scan through the wavelengths. We have the 700 nanometer side as the red side, 400 nanometer side here is the purple side here. What he found was if he did this to elements, he actually found elements actually gave rise to line spectra, or a line spectrum. So for a line spectrum, as the name suggests, you have individual lines or individual bands of color. Individual bands, and we're going to see these ones here correspond to our electron transitions. It corresponds to what electrons are actually doing on the element itself. Now again, it's a little weird to think about here. Well, if I just have a sample, let's say it's a sample of hydrogen gas, why would this thing here be colored? You're right, it's totally not. In the lab, however, what we're going to do is we can actually set this up in a discharge tube. We can actually use high voltages. If I manage to send in the right amount of energy, I'm going to do this with electricity. I'm not actually going to see the electricity. What I'm picturing here is if I do the energy level diagram of hydrogen here, Bohr model, well, hydrogen should only have that one electron in the first shell. Hydrogen's nucleus is down here. For the electron being on that shell here, it's yay far away from the nucleus. It has this low energy level 1. It does have actually all the infinite shells available, 2, 3, and 4 and all that. It's just that the electron has no desire to go into those other shells because it wants to be close to the core. Now what I'm doing is I'm exciting these electrons with electricity. So if my electricity is fine-tuned enough, this electron can actually absorb that energy. We saw that term yesterday. And what we're going to do is we're going to actually jump that electron up into some higher shell. It's going to jump farther from the nucleus into some excited state. So let's say for argument's sake here, I managed to take that single electron that hydrogen has. I'm going to use electricity. I'm going to send in all forms of electricity. If it's exactly the right energy, this electron can actually jump up to a higher shell. So that's like in the Bohr model here, it's like having the electron on the third shell. It doesn't necessarily want to be there, but it has so much energy it's just dancing around for a little while. So there's my electron. That process there was absorption. We'll come back to that absorption section a lot more in chapter 3. For us in chapter 2, we're going to focus more on the latter case here. We know that the electron doesn't really want to be here for the long term. The electron ends up dancing around for a while, ends up getting bored, and ends up saying, wait a second, there's shells that are closer than me, and it actually wants to revert down to a more closer to ground state. Being on a staircase, however, I have many choices on how I'm going to emit. So what could happen here is, for sure, I can, since I jumped, in this case here my absorption was, I can shell 1 to shell 3, right, shell 1 up to shell 3, I can for sure jump n equals 3 down to shell number 1. I can go this electron here, I can completely just jump down to shell number 1. Based on a conservation of energy argument, I have put in energy to get this electron up to that higher shell. Even though the electron is still stuck on the atom, the electron is not leaving, the electron is just jumping closer to the core. As it returns closer to the ground state, closer to a lower energy state, it has to give me that energy back. We have put in that energy using electricity. Turns out, usually when this energy is given back, it usually gives me back the energy in the form of light. So let me just write this down in words for you here, especially for this latter process. As electrons fall to lower shells, that's emission, right? That's the big name for this. As they fall to lower shells, energy is released as photons or as light. And what's really special here is those photons, even though we picture all photons here as just a packet of energy, as just one particle of energy here, as that photon leaves, it's going to have a very unique energy signature. Because this is a very well-defined gap, 3 to 1 is a particular delta E, that gap you're going to say is very big. So as this photon here leaves, it's a light particle that leaves, right? The electron is stuck on. As that light particle leaves, it's going to be more on the high energy side. So this is going to be the 400 nanometer side. I'm going to have a rough 700 nanometer side. Every time my electron jumps this gap, it's going to always produce a purple color photon. It's always going to produce a photon with a very unique energy signature. What were my other choices though? I didn't have to necessarily go 3 to 1. Well, what if instead I took the detour? What if I went 3 to 2 first, right? That would be still emission. I'm falling to a lower shell. But this time when I fall, you notice that that energy gap here is a lot tinier. I also will release a photon because the photon's energy is a little bit tinier. The photon, the light particle that gets released, is also going to be a lower energy color. Lower energy means higher wavelength. I can get more to this purple side of the spectrum. And there we go. Bohr did this experiment. He actually saw, this one here is a line spectra. You might see the band. I might see the red color. I might see the purple color. And yet, I don't see any in between. I don't see the purple transitioning into the red. In fact, that one there is not done yet. Energy shell 2 becoming shell number 1. As I fall 2 to 1, I actually give off yet another color light. This one here is sort of moderate in energy. It's somewhere in between the purple and the red. And we're going to see maybe more a greenish color here. This is still a line spectrum here. The line spectrum, let me write this down in words here. These energies correspond to the gaps on the element's staircase. So remember, Bohr didn't know about all this discrete stuff. He did this experiment, he saw a line spectrum, and he ended up concluding, well, not only electrons have some limit on each shell, it's more like a staircase, so that, sure, an electron can jump up and down the staircase, but because it can't fit anywhere else, it can't give me sort of some in-between energy. every time it jumps 3 to 1, it gives me only this color. Every time it jumps 3 to 2, it only gives me this color. It's not actually able to give me any other colors there. There is one other note here. Remember we were saying the energy shells actually converge. Energies converge at the high energy end. You can look back at our yesterday's lesson for why that was the case. At the high energy end, this was due to finite attraction. There's a limit to how far your protons can actually attract it. Finite attraction to the nucleus. Because the energy shells are going to stack up, as I start looking at transitions, as I go, let's say, 4 to 3, 5 to 3, 6 to 3, 7 to 3, those transitions themselves, although they're discrete, although they're very unique energy signatures, they'll also get closer together. We're going to find that these energy bands, yes, I'm going to still be missing color, but if I had the other lines here, those lines would also get closer together. That also is a nice conclusion and support for energy shells getting closer together. Every element actually has its own discrete energy gaps. You can imagine going to helium. Helium has another proton here. Maybe its energy shell 1 is lower. But helium also has its own unique staircase. As the electrons fall down its staircase, it's going to give you a very unique signature. Astronomers use this all the time. They point their spectroscopes out into space. They figure out what sort of color lights that they get, what intensities they get it at, and they can actually figure out what elements that star is actually made up of. I'm going to finish off this lesson here. It's a little bit confusing, if it wasn't already yet, but it's a little bit confusing to just go, I'm an electron on this floor. What are all the ways for me to actually fall downwards? If you go on to chemistry, we get into sort of phosphorescence, fluorescence, things like that. It's actually a little bit easier just to categorize for ourselves. Let's focus on a ending position. Let's focus just on shell number 1, and let's look at all the transitions that go directly to shell 1. So what are those transitions like? 2 to 1, 3 to 1, 4 to 1, 5 to 1. As long as I focus on shell number 1, you'll notice because I'm dropping all the way to 1, I will definitely have the biggest energy gap. This is in the notion of drawing what's called a series. Right? I'm going to have roughly my visible region, my UV region. Whenever you do this, you want to be careful to label your sides. So this side I have as the more energy side. This side here is the less energy side. If you look at those transitions that I just mentioned, so instead of being that one electron and how many ways can I fall downwards, I'm going to focus just on ending on shell number 1. I'm going to be on any shell n and I'm going to drop to 1. I could be 2 to 1, right? So 2 to 1, that's a big gap. I'm going to be in the UV region. I could be 3 to 1. I'll actually list these for you here. I could be 3 to 1. That's even a bigger gap than the 2 to 1, so even more energy, 3 to 1. I can go 4 to 1, even bigger energy. Again, it's a band, it's just one single color for that particular transition. I can go 5 to 1. But what you're noticing, like I just mentioned, because of this convergence, because of this thing here getting closer together, we're going to find that these bands here themselves also get closer together. In this case here, we refer to for the hydrogen atom, so I'm going to emphasize that. For the hydrogen atom, when you start categorizing in this fashion, we're going to call this one here the Lyman series. The Lyman series is dropping to n equals 1. Now, what are my other choices? I could hypothetically, let's say, have my energy shells here. I could hypothetically be focused. What if I focus just being on n equals 2? Now, I know I wouldn't be done then. I would still need to fall 2 to 1. 2 to 1 would be in Lyman series. But let's look at all the transitions. Let's look at, if I go 3 to 2, that's my first gap. In comparison, this gap here is a lot smaller than that 2 to 1 gap. So, because that gap is smaller, we're going to be pushed over, instead of being in the really energetic UV region, we're going to be pushed over in the visible. They always like asking this question, draw the emission spectra for hydrogen in the visible portion. I want you to draw here for 3 to 2. That's going to be a red color band. What if I go 4 to 2? Now 4 to 2 is going to be a little bit bigger. Maybe that's going to be a Roy G. Yeah, it's a green color band here. Maybe that's 4 to 2. Again, it is a line spec, so we don't get any of the in-between transitions. Let's tack on 5 to 2. Because the energy shells themselves are converging together, the bands are not really getting as far away from each other to the next band. This is 5 to 2. And then lastly, we have 6 to 2. Right? 6 to 2 would be even more energetic, but also getting closer together. That purple band is 6 to 2. Could I hypothetically go, that's called the Balmer series, by the way. Balmer is falling from any shell n down to 2. Could I have 7 to 2, 8 to 2, 9 to 2? Of course you can. Those ones there would actually be energetic enough. They're sort of fringing into the UV region. So usually for the emission spectra, we just draw those 4 lines. They need to be closer together on this axis. And just for completeness sake here, we could similarly go, well, what if I ignore step 2 and step 1? What if I just focus on step number 3? So I'm focused in all the transitions that land me here. And again, you sort of get the idea. Because the energy shells are getting closer together, in general, these arrows are tinier than this one. They won't even be as energetic as visible. They're going to be into the IR region, but they also will have a steady converging together because the shells are stacking up close together. This one here is called the Paschen series. Paschen series is falling from any higher n value to a shell 3. Right? So have another look at that there. We'll pick it up from there tomorrow. Thanks, guys.